In this video, we are going to begin our discussion of section 12.3. This is going to be the extension of arc length and then taking arc length and making it in terms of parametric equations, like making equations, I said that reverse, making equations in terms of arc length. So recall from Calc 1, this was the formula for arc length, and hopefully somebody at that point explained that formula and where it came from. I'm not going to do that here since that is a Calc 2 topic usually, but to extend to 3 dimensions, all we do is add that third component. Remember, this is finding arc length given the set of parametric equations. Given a set of parametric equations. That's the most relatable here with talking about vector value functions, because typically when we talk about a vector value function, we're talking about some function f, component I, some function g, component j, almost wrote k, h of t, some function h, and k. Right, that is why it would make most sense to relate back to the parametric equation idea when we're talking about vectors. Now, what I want you to notice, if we define it that way, that formula is great and all, but we actually can make this easier for us through at least this chapter. Notice, take the derivative of all these, like we talked about this chapter. We just take the derivative of the f function for I, derivative g for j, and h, we just take their derivatives, and that's what they become for that. Then, notice if I take the magnitude, right, the length of this function, that's taking the square root, taking f prime of t, and squaring it, and adding it to g prime of t, squaring that, and adding it to h prime of t. And most of you guys are probably already noticing what I was doing here. That's exactly what's in our integrand. So what that means is that L, right, what we were just talking about, can be thought of instead of using that crazy formula there. Even though we're going to be doing it anyway, this will make it much easier to remember. And it looks like a jumbled mess, but it's just, if you think about it, and I feel like it makes it less overwhelming too, because when I think about finding a magnitude of a vector, I can do that. And most of the time, we're going to be plugging things into that vector to get the stuff inside anyways. So what this gives us, we have two different things, and the second thing is not going to make much sense to you until we get to it. This gives me arc length given two values, meaning if I want to know how far on the curve from A to B, I can find that from this formula. It also will give me an arc length function. We're going to call this, we'll talk about it in this section, S of t. S being arc length. All right, let's get an example of this arc length under our belt with an example here. Instead of thinking of each component, we can just think of taking the derivative. So that's negative 2 sine ti. We get minus 3j, and then minus 2 cosine tk. All right, and then we just take its magnitude. All right, so we're going to start seeing some patterns of magnitudes in our sines and cosines here. So if I square each component, I get 4 sine t plus 9 plus 4 cosine squared t. That should be a squared on that sine. We squared every single term. Now, what I want you to notice, this factoring, you can eventually probably skip this factoring part, but I want to show it because so many people mess it up front when they try to do it. Notice that both of those had a 4. So I'm going to factor out a 4. That 9 is still there. Inside there, though, sine squared plus cosine squared is a 1. Right? That's that identity times 4, so we get 4 plus 9, which means this is a square root of 13. So that crazy formula that we were looking up there for arc length, we can actually find that length now, going from 0 to 2 pi of it's the magnitude of the derivative of our vector value function dt Well, that's extremely easy now if we think about it this way, because I just that's a constant. So this is square root of 13 times t ran from 0 to 2 pi. So we can see what this answer is going to be. It's this with that pi. How do we want to write this? 2 pi square root of 13. I think that's probably the best way to look at it. All right. So it makes that arc length formula, thinking about it this way, much simpler. Even though we're doing exactly what we would have done by following this formula here, it just feels like much less because you guys have had a crazy 2 weeks of magnitudes. So the magnitude should feel more familiar here rather than having to memorize that formula. Now, let's get another example in. These are going to get pretty long because some of these magnitudes take some space up. So I would recommend writing kind of small. I'm going to try to do my best to do that as well. Let's find the derivative of each component. I'm going to start getting, no, let's keep writing it out. F of x, in this case, is going to be e to the t cosine t, right? So f prime, and I put an x, I'm fighting a bunch of habit there, f prime of t. So this is the derivative of negative e to the t is negative e to the t cosine t. That's the first one. Then I leave the negative e to the t, and derivative of cosine is negative sine, so I'm going to get a plus sine t. I can factor out, I'm going to factor out e to the t. The reason I knew not to do a negative is because only one of them is negative. And then I'm going to flip my sign, so I can put the negative with the cosine with the subtraction. So there's f prime. G of t is the middle one, which is e of t sine of t. I take the derivative of that, I got c prime of t, right? Derivative of e to the t is e to the t, and I leave the sine of t, plus I leave the sine of t, and I take the derivative of sine to get cosine, and I can factor out an e to the t for that as well. Right, that's f, g, h is that last one up there. So h of t is 2 e to the t. So if I take the derivative of that, h prime of t, we get 2 e to the t. That's nice. All right, so we have that. That will give me my r prime. We get e to the t sine t minus cosine t I plus e to the t sine t plus cosine t j, and then the last component being a nice pretty 2e to the tk. All right, we're going to have to take a magnitude of this. So I'm going to rewrite this so you can see this. I'm going to take an e to the t out. So this is now sine t minus cosine t I plus sine t plus cosine t j plus 2k. All right. So when this goes into the magnitude, and think about the product for a minute with the squaring everything, right? That e to the t is going to be squared and then square rooted, and I can separate it from the rest since it's being multiplied. So my magnitude here, when I do that, I can just pull this e to the t out front and then put the rest of this inside. All right, so we get sine squared, sine t, oops. All right, I want you to take close note to this because I'm only going to do this much multiplication one time. It's going to show up later, and I'm not going to do all the multiplication. I'm going to take a shortcut. So everything gets squared and added together. All right, so this is the part I'm going to start trying to write little. Okay, so doing this, we get, that's foiled. So sine squared, FOIL, I hate that acronym, but multiply it out. We get minus 2 sine t cosine t, and then plus cosine squared t. The second binomial being squared, it's all positive, so we get sine squared t plus 2 sine t cosine t plus cosine squared t plus 4. Right, we have some terms that, two terms in there that cancel this one, that one. So we have e to the t. Then we have, we're going to have, I'll take the square root, 2 sine t, 2 sine squared t, plus 2 cosine squared t, plus 4. All right, you can see how I got that. And then we can factor out that 2. All right, 2, and then sine squared t plus cosine squared t plus 4. Then we get e to the t. That's going to be a 1, so we get the square root of 6. All right, so that was just the magnitude. That's where most of that work will come in for these problems. We want the arc length from 0 to 2 pi of r, I'll write this out, r prime magnitude dt. Well, that's just square root of 6. I can pull that out. It's a constant, 0 to 2 pi. And then I can just put e to the t here, d to dt. That is a great integral to have. We just get et, and we're going to run that from 0 to 2 pi. Now be careful here. There's a mistake made by students all the time. We're so used to seeing that 0 and just ignoring it because usually zeros make them go away. In this case, it doesn't do that. This is e to the 2 pi minus e to the 0. Well, that is square root of 6, e to the 2 pi. That's a minus 1, not a 0. So be careful there. So that is that length. You can plug it in your calculator. That is the exact length of that curve from 0 to 2 pi, whatever that may look like. But if we were to measure the length of the curve, that's what we'd come out with. So in this section, we focus on a technique that we're going to use rarely, but they like to teach it. We're going to use it later briefly, and it's going to help us out tremendously in Chapter 15. If the curve is smooth, remember that just means all the derivatives are really nice, we can reparameterize, I struggle with that word, by arc length, but why? The three reasons being, the vectored value functions, remember we have like our origin, and then we have like these arrows that point to the curve, and it tells us where like to go next, right? And the way we have to think about these curves is like always go back to the origin and then always point, and go back to the origin and then point, and back to the origin and then point. Like that's how this is defined. But if I define it by like how long the curve is, and I have this space curve out here, right? And I just want to know if I start here, right? I can figure out where I'm going to start and go along this curve. Well, I can come up with this function here. If you tell me, hey, I only want to go 3 units. Well, okay, I'd go 3 units, right? And then this value, it would spit it out, like where the point is. So that makes it nice sometimes. If I can give you an arc length, hey, I want to know 5 units from this point to this point, I can actually give you that second point on where 5 units would be, or 3 units, however we want to think about it. Sometimes doing this, changing to arc length will make the formula simpler. That's always ideal in mathematics. And then we have other thing here that we'll finish here in a moment. R prime of S is arc length, will always have magnitude R prime of T. I think that's supposed to be an S, so we'll come back to that here in a moment. Okay, so let's do an example of this starting off. We are going to find the arc length function. This is not L, right? This is not L, but rather it's S of T. Okay, how we do that is we are going to use this definition, except for what we're going to do is make our bounds not defined. We're going to define one of our bounds, but not both. So first thing we're going to do, just like if we were doing arc length, we're going to do R prime. So I'm going to switch to component form here because these are all nice. So -3 in the end. There we go. right? And then we can also find the magnitude of this, right? Especially if we're heading towards an arc length road. This is the square root of 1 plus 9 plus 9, which is the square root of 19. Now we know that I can find the arc length by putting that in a to b, but we don't have an a to b. What we're going to do instead, we're going to say, hey, some number that we're choosing a, and we're going to change this to t. And what we're going to do is we're still going to put this magnitude here, and I'm going to leave this blank for a moment. And it's going to be the arc length, but instead of from a to b, we're going to do a to some unknown t, creating a function, right? If I have some unknown that I'm going to plug in, it'll tell me that. Now, since t is my input, the variable that goes in our integrand and dt usually, we're going to change it to something else. We're just going to make it a u. We don't want to use t since we're going to plug in t here. We can't have those like conflict with each other. Now, in this case for this problem, what we're going to look for is we're going to create that functions there, but that a, let's write a note here. A is where t begins. Replace t with, and it's called a dummy character, but I'm going to put u. Oh, all right. It could be whatever you want. I had a friend back in undergrad for me put smiley faces on all his variables for a proof. I'm sure the professor loved that. Probably not. But he did it anyway. I don't care what you put there. You can choose whatever you want. Some letter would be great. So if I create it for this function, or this problem, we're creating a function. T starts at 0, so I'm going to put a 0. It goes to t. I don't replace t. I'm creating this function. Then I know that if I take the magnitude of the vector that was given, that's just square root of 19 du. Careful not to put a dt there. Now this becomes, and you can see this pretty easily, s of t becomes square root of 19t. Right? It's pretty easy integral here. Now I'm going to call that s of t just an s, and I'm going to solve for t. So what we have done is we have found a formula that changes all our t's to s, changes time to arc length. So what this function would look like now is r prime of s, r prime of s, and I just go through and I change the function with that for t instead. It is not pretty, by the way, but now this function would tell me if I want to know where I would be on this curve when I go 3 feet forward. I could plug into this function, plug a 3 in, because that would be my arc length, and it would tell me the point that I would be at on my curve. Like I said, this isn't prettier. We weren't looking for that on this one. We were just looking for how to do one of these problems. But sometimes, not always, it'll make simpler. Like I said, it also allows us to think in arc length instead of time. And then if we take the magnitude of this thing, let's see, and I do need to point out this will be s is greater than or equal to 0. This makes sense because we're talking about arc length. All right. This r prime of s, this should be an s right here. So go ahead and do me a favor. I'm sorry, that's a typo. This will always be a tangent unit vector. So this will always be 1. Right? And that's talking about the rate of change with respect to arc length. Okay. Right, let's do one more arc length function problem. We are going to come up with our arc length here. This is a problem we have already done, so I'm going to go ahead and give this to you. R prime of t is radical 3 e to the t. We have done this at some point this semester. Just to make, I'm not going to make a whole video where we have to do that again. There is another example after this with one more magnitude one, and it gets pretty gross, so we'll do that. All right, so we have this. We can actually find the arc length function. This is s of t equals, and we start where t starts at 0 to t. And then we plug that in. This is going to be radical 3 e to the u du. All right. This is nice and easy to see. We get rad 3 e to the t ran from 0 to t. Well, that would just plug that 0 in. We'd have a u there, meaning plugging that in. So that's what we get for that. Oh, we need to be careful with that actually. So I actually made the mistake I was warning you of. This is just that same thing from 0 to t. And my brain, it's easy to get this way. It's so easy just to ignore it. But we have to do e to the t minus e to the 0. My brain was like, oh, that's a 0. It's not. It's a 1. Super easy to get used to thinking that. Just be careful. All right, so we have that now. And we have this as S. And now remember, the whole point of this is to find an equation relating T and S. That way we can convert. Okay, so if I start solving this for T, I would divide by the square root of 3, and I would add 1. That would give me e to the T. All right, now if I were to go back and replace everything in my R function, let's do that. Everywhere there's an e to the t, I'm going to put an s over rad 13 plus 1 times cosine, and then I got to figure out what is t. Well, this is just an ln on both sides. So I get ln of s over square root of 30 plus 1 equals t. Feel like I made an arithmetic mistake somewhere. Nope. Okay, so we're good. All right, so that is what t is. So I'm going to put, let's call this, no, we'll write it in. I almost was going to be lazy, but we'll write it in. S over rad 3 plus 1. Right, that's that first component. The second component had an e to the t, so I'm just going to put S over rad 3 plus 1. That's that e to the t. And it was sine t, so sine. And now we have that ln. Oh, that ln should have went in there. Let me drag this whole equation over. Ln of that. It's not pretty. Ln of s over the square root of 3 plus 1. And then our last one was just e to the t, so we get s over square root of 3 plus 1. That is the vector in terms of s, in terms of arc length. Is it pretty? Absolutely not, but it does give us two options for a unit tangent vector. We could use this formula, we could use the other formula. If I were to take the magnitude of this thing, I actually get the unit tangent vector. So it's kind of interesting. Take a look at that if you'd like to explore that option. We have one more example here. I'm going to work pretty fast through one part of it, but there is a trig sub in this integral, and I would like to give you a reminder of how a trig sub works. Okay, so the first thing we're going to start off if we're finding arc length is we need r prime. So that is a 2t, and then that's a product rule. So this is going to be cosine t plus, it's going to be a cosine, so we'll get a minus t sine t. Derivative of t sine t will be sine t plus t cosine t, because that one doesn't change the sign. So there's r prime. And I can find the magnitude now. I'm going to need that to put in my integral. All right, so we get 4t squared. And then we're going to have this stuff squared out. So this is going to be similar to a problem earlier, but not exactly. Squared sine t plus t cosine t squared. And then we have to work all this out. All right, so we get, this is going to be where it's going to be quite a bit. So 4t squared plus, okay, we get cosine squared t minus t cosine t sine t plus t squared sine t, sine squared t. Then we multiply that binomial squared out, sine squared t, plus t, two of them. We're going to have two of those. We're going to have two of those here too. So minus 2t, this last thing here, plus 2t cosine t sine t, plus t squared cosine squared t. That's just multiplying all that out. All right, we lose two terms. We lose those. So we get the square root of 4t squared, and then we're going to have plus cosine squared t plus sine squared t. We have a pair. And then notice the other ones will have a t squared, so I'm going to factor those out of that. T plus cosine squared t. So we get, we're almost there, 4t squared plus 1 plus t squared. There was a 1t squared, leaving us with the square root of 5t squared plus 1. All right, I'm trying to find arc length, so I just got to do 0 to 1 here. So this is L equals 0 to 1, and I get to throw that in here, and this is what causes all the problems. If you have a table and you want to use a table, kudos, please do it. The table will be provided. I am going to do a trig sub review here. To do a trig sub, first we need to get it in the right form. We would have the square root of 5t squared plus 1 squared dt. This helps us see. All right, knowing it's a trig sub, I'm going to go over here with the triangle. All right, my right triangle. And looking at what I have there in my integrand, that looks like a hypotenuse because it's a plus. So I'm going to put the square root of the square root of 5t squared plus 1 squared. This is going to tell me what the other sides are. We always want to keep the variable on top. So if this is theta, it's always like this side over that side, or it's going to be this side over that side. But we're not really going to think this side over that side or this side over that, because we get into our inverse or reciprocal function. So with all that said, I'm going to put the square root of 5t here and the 1 here. Now with this, we do get some equations from it. I have tangent of theta. That's like the cleanest thing I'm going to get to relate there, is it's going to be the square root of 5t over 1, but I can drop the 1. I can now multiply or divide, so I get 1 square root of 5 tangent theta, solving for t. Taking the derivative here, like in the trig sub, so what we do is we draw the triangle. We find the trig sub that relates the other two sides. We solve for t. Then we take the derivative of both sides. dt equals, it's going to be the 1 over the square root of 5 secant squared theta d theta. All right, so now we're going to start replacing everything. So we get the the integral from 0 to 1 of this becomes tangent squared theta plus 1. That's using the trig subs that we had over there. All right, times, and I'm going to replace, now we can replace dt with all of that. 1 over the square root of 5 times secant squared theta d theta. Okay, then from our trig subs, I know the square root of tangent squared plus 1, that is a Pythagorean identity. That's actually secant theta, times 1 over the square root of 5 times secant squared theta d theta. And then now I'm going to move the 1 over the square root of 5 on the outside, 0 to 1. I get a secant cubed theta d theta. I'm going to use a table because this answer is extremely gross. We get 1 over the square root of 5. Okay, and then this is what the just integrand, not plugged in or anything. 1/2 secant theta tangent theta plus 1/2 ln the absolute value of secant theta plus tangent theta absolute value. You do not need to have that memorized. I don't have it memorized. Now the problem is right now is that 0, 1, 0 and 1 are t's, not thetas. So I need to either convert my t's to thetas or go the other way. We're going to plug it all in for the answer anyway. But usually with trig subs, it's easier, I think, most of the time, just to see what we already have this value. Well, now I can just get a secant. Secant theta is, that's related to cosine. Cosine would be 1 over this side. So a secant would just flip that over. So a secant theta is just going to be the square root of 5t squared plus 1. That's 1 over cosine. So find cosine, flip it over to get secant. So now I can actually go through and plug all that in. So we get 1/2. Secant is the square root of 5t squared plus 1. Tangent is the square root, what was it? Square root of 5t plus 1/2 ln. You could have also converted the other way, right? Back everything to theta. 5t squared plus 1 plus d squared of 5t. I think that's it. And then now we can do 0 to 1. Right, plugging this all in. I'm going to have you guys trust me on this so the video's not too long because it's already pretty long. We get that over the square root of 30 plus ln square root of 6 plus square root of 5. If you work this out, it's not hard to follow. That should be a bracket there. All right, that is it. That is the arc length from 0 to 1 of that function. Trig subs are difficult. They do definitely take some time. I would refresh yourself on it. It's good to know. It's going to make you really great at integration. And like I said, it's not going away for the semester. I will be providing tables on some parts. This test, there will be a table on the exam for you to use.